Hola, buenos días a todos. Hoy jueves, cuarto día de esta escuela, tenemos la tercera charla del profesor Roni Harnik, que como seguramente vieron en las lectures anteriores, es una linda combinación entre teoría y diversión. Así que, bueno, le agradecemos una vez más a Roni por estar acá. Roni, for the non-Spanish people here. So we will have the third lecture from Roni Harnik. As you have seen in the previous talk, Roni's lectures are a very nice, very perfect combination between theory and fun. So enjoy it. And Roni, we are all set, so go ahead.
Thanks. Theory and fun.
Yeah.
So there's theory and there's fun, two separate things, and I managed to mix them.
Yes,
I'm kidding.
Right. Yes.
Good. Welcome everybody for lecture number 3. So in lecture number 1, we got a little bit of introduction for what the language is, quantum field theory. In lecture number 2, we got to the meat, which is the standard model. And we spent some quality time with the standard model Lagrangian. I should replace my pen to the one that works here. Scribble, yes. So there's a bunch of terms. They're qualitatively, we sort of gave them names and what jobs they do for us. But we're not done. So we're going to get to know some of these terms a little bit more closely. And having brushed through a little bit of QED and a little bit of QCD, we're now diving into the electroweak sector. And that's the part that's important for neutrinos, because the neutrinos only interact through the weak force. They do not interact with the photon because they're neutral, and we're going to derive that. So we're going to focus on this line, and before that, we're going to focus on this line, which is the dynamics of the Higgs. So the Higgs breaks the rotation symmetry. This is the cartoon. The Mexican hat potential is the cartoon of this that is most often used, and it is extremely useful to get a grasp of what's going on in terms of the fact that the symmetry breaking vacuum has a lower energy than the symmetric point. But I ended by showing you what field space looks like a little bit more accurately, which is that SU2 is like SO3. There are 3 generators, so it's useful to think of it as rotations, 3 Pauli matrices, if you like. And in terms of field space, what this potential does is it pushes the vacuum away from the symmetric point, which is the center of this block sphere, to some random point on the globe, and there's still a leftover U1 symmetry, which is rotation around that point, if that were the pole. So this breaks SU2 down to a U1. The Higgs field, remember, is 1 under QCD, a 2 under SU2, but it also carries hypercharge. So it also breaks a hypercharge, and then a linear combination of hypercharge and the leftover U1 is the U1, which is our photon. So SU2 cross U1 breaks down to U1, and 3 gauge bosons get a mass. Now, one thing I didn't have time to tell you is that there's a qualitative difference between a massless gauge boson and a massive one. the qualitative difference is the fact that 3 is not 2. So a photon, the photons that we see have two polarizations, right? Vertical or horizontal, left or right, depending on the basis we choose to expand in. But there are only two polarizations. There is no longitudinal photon, famously. A massive gauge boson, if you think about it, is, again, it's a vector. So if it has a mass, we can go to the rest frame of that vector particle. And obviously, the spin of that particle can point in any which direction. So there are 3 degrees of freedom. There are 3 polarizations. So a massive gauge boson has an extra degree of freedom, which is the longitudinal polarization. So how is the gauge boson going to acquire another degree of freedom? And the answer is here it is the gauge boson, the Higgs boson itself. This is a complex scalar, right? There's a real and an imaginary part, and it's a doublet. So there are 4 real degrees of freedom. 4 degrees of freedom. And we need only 3 extra ones. So in order to give the gauge bosons a mass, 3 Higgs degrees of freedom. And the words that we use to describe this process of the Higgs giving its degrees of freedom to the gauge bosons to give the mass, the language we use, that they are eaten. And I'm not, for lack of time, I'm not going to go through the mathematics of eating Higgs by gauge bosons, but just in terms of the arithmetic of degrees of freedom, that's how it works. So that's just to put your mind at ease that the degrees of freedom are coming from somewhere. So notice though that we had 4 up here and 3 are eaten, which means that 1 degree of freedom was left over as a scalar. And that is the Higgs boson that was discovered. Its announcement was, the announcement was made on July 4th, 2012, in the middle of the night for me. So that's that was the last degree of freedom of the Standard Model that we found. Good. So let's decorate the process of giving the gauge bosons a mass. Let's decorate this with some equations. So where is so first of all, starting from the potential in equations, it looks, this is a convenient representation of this equation of this potential. Sorry. So obviously, the vacuum expectation value for the field squared is going to be just v squared from this potential. Or in components, right? The Higgs is a 2-component beast. It's non-zero, so its non-zeroness should go somewhere, somewhere distributed between the top and the bottom component. So let's put it here. I'll put it at the bottom. At least in my note, it's in the bottom. Maybe later it'll migrate to the top. The point is that this is an SU2. There's an SU2 rotation. So this is an arbitrary choice as far as the symmetry is concerned. And in fact, the Higgs, this is what picks which degrees of freedom are going to eventually become neutral and which degrees of freedom are going to be charged. So in previous slides, for example, we chose to, for example, here we put the neutrino in the first entry and the electron in the second. That was an arbitrary choice that we made in anticipation of the Higgs picking picking a particular direction. Okay, so the Higgs is the kingmaker in terms of who's neutral and who's charged. Okay, so where is the Higgs needs to give a mass to the W and Z by breaking the symmetry. Where do they talk to one another? Well, they talk to one another through this term, right? So we square this to get the kinetic term. So let's write this out. The covariant derivative is just this. So now this is a covariant derivative acting on the Higgs. So we'll get a piece. The Higgs, as you see above at the top of this page, is charged under SU2 and U1. So we'll get a contribution from the SU2. There are three. So the three Pauli matrices, which when they're acting in an internal space, sometimes we call them a tau instead of a sigma. So there's sigma 1, sigma 2, sigma 3, or tau 1, tau 2, tau 3. So that's what this A is. This A is going 1 through 3. And there is the G prime. So G is the coupling of SU2. G prime is the coupling of the U1. G prime is a bit smaller, as it turns out, times B mu. This 1/2 is coming from this 1/2, from the charge, the hypercharge that we assigned to the Higgs. Good, and this is acting on the Higgs field, but let's pick the vacuum expectation value, right? So we're going to act on this VEV. So now the derivative just goes away because this is the piece that is not varying in space or time. The vacuum expectation value will be uniform in space and in time. So we can ignore the derivative and we just get the coupling of the gauge bosons to the vacuum expectation value. So let's write this out. This is now, these are 2 by 2 matrices. So let's write it in matrix form. So we'll have a big matrix. It will multiply that. So let's see, we have on the, from the, on the off diagonal, we have a contribution from the off diagonal. So tau 1 and tau 2 are off diagonal, either a 1, 1 or an I minus I, right? So we'll have a W1 minus I W2 up here. Sorry, this is a mu. Down here, there's the same thing, only with a plus sign. So this is, not surprisingly, a Hermitian matrix. And on the diagonal, we have a contribution from the B mus, which has the same sign. And from the third Pauli matrix has a 1 minus 1. So there's a GW3 and a GW3, but with a minus sign here. Good. So this is going to multiply this VEV. And now, in order to get the mass term, we will take, so we're just going to pick the second column here because there's a 0 upstairs in the vector, and then we will square this. So this will contain, and I'll leave this as an exercise for you to write out. There's a W plus times W minus, where here I've defined W plus minus as the W1 plus minus IW2, as you would expect. So the W plus and W minus are going to be raising and lowering in SU2 space. And the plus and minus don't only correspond to the fact that they're raising or lowering, or that we're picking the plus and minus in this equation. It's also going to be the electric charge of this actual particle, right? There's a squared here. And there's another term, which is the mass of the neutral gauge bosons, and the combination that shows up is this, right? Essentially, this is essentially this combination here that appears with a minus sign, and I only good. So that was just a little bit of manual labor. Here I've copied the same thing just to the top of the slide. So this piece here is the mass for the W boson. And this is the mass of the Z boson. So first of all, we've derived here what the masses of the essentially 4 gauge bosons in the problem are. The mass of the W is 1/2 the gauge coupling times the VEV. So it's if the VEV would have gone to 0, the W would be massless. If the coupling of the W to the Higgs would go to 0, the W again would be massless, as expected. The mass of the Z boson is, now it's getting this term needs to be properly normalized, but it turns out that the mass is, there's a contribution from SE2, and there's a contribution from the U1 coupling times V. This gets square rooted if I'm writing the mass and not the mass squared. And the mass of the photon is going to be 0, famously. We don't even need to write it out. The photon, by the way, is whatever is orthogonal to the Z, right? Which is, well, we swap the coefficients and put a minus sign in between, and we normalize properly. And we get G prime W3 mu minus G B mu, and I promised you that I'd flip the sign, so now they're orthogonal. And this is the photon. The electric charge is just going to be the hypercharge. And I'm sorry, I did not write this in this note, so I don't make any promises about factors of 2 and signs, but the eigenvalue of the third, right? The photon is getting is partially W3, so there will be a tau3, right? The eigenvalue, the appropriate eigenvalue. If it's the top component, it's a plus. If it's a bottom component, it's a minus 1/2. Okay. So we now know that the photon is massless, or we've identified the massless degree of freedom and how it couples, and then we call it the photon. as an aside, a prediction of this theory is something called the rho parameter, which is just this combination, mw squared over mz cosine of the Weinberg angle. The Weinberg angle is just the mixing angle involved in diagonalizing this the neutral matrix. So the Weinberg angle is the sign that appears in the definition of the photon. This is defined as sine of the Weinberg angle. And in the standard model, this is 1, at least at tree level. So this has been measured, tested very well, and this this agrees. I didn't tell you what the value of the Weinberg angle is. I seem to remember that the sine squared of theta w is roughly that. Let's put a squiggle here. Good. So all we've done is we took this term, the kinetic term for the Higgs boson. Through it, the Higgs Vev couples to gauge bosons and gives them a mass, and through that falls out one massless photon and two massive gauge bosons. Okay, this is a school about neutrino physics. So let's think about the neutrino and how it couples. Remember, Pedro's lectures started with the charge current coupling of the neutrino. So let's derive that now that we've put all this in place. So again, I've written down the covariant derivative for any field, and we will. I need to write in blue. We'll pick sigma plus minus as sigma 1 plus minus I. And you see I'm switching between sigmas and taus a little bit sloppily. I apologize. And sigma 0 is sometimes sigma 3. These are synonymous. And now in the basis that we had before, remember the left-handed lepton will have two components. The top one we'll call the neutrino, the bottom one we'll call the electron. So now we can write out the kinetic term for this field, and we'll pick only the off-diagonal piece. This will be the charged current, the thing that couples the top to the bottom here. That will obviously come from the W plus or the W minus. So there turns out to be a square root of 2 here for good measure. And you see from in putting, we're essentially putting this between two of these, right? So only the sigma plus and sigma, the tau plus and tau minus will generate that coupling. See, now I was really sloppy. This is bothering me. Apologize. Let me get rid of this. This was supposed to be taus and not sigmas. So I'm removing this from the The sigmas that I'm writing here are the sigma, the space, the real spin matrices, and the taus act in the internal space. And on the side here, I mixed those two up, so I apologize. And so this one takes the neutrino to the electron, and there's one that takes the electron to the neutrino, and that is done by the W of the other sign. Okay, so the coupling of the W, the famous charge current interaction that is used to produce and detect most neutrinos, is coming from this kinetic term of leptons. Good. So let's write this as a Feynman diagram. Let's see if I can make some straight lines. So we will have the electron will couple to an electron neutrino. The muon will couple to a neutrino that we'll call the muon neutrino, and the tau will couple to the tau neutrino, right? And maybe we want to put bars here. So first of all, here we've made contact with Pedro's talk again. So Pedro is happy. Very good. This is Pedro. Hold on. You shouldn't have a sigma 2 in the last term. So yes, of course I should. And it's not in my notes, but thank you. There's a sigma here. Fantastic. Yeah, so this is a vector. This mu was left dangling here, and this was not invariant. So now this is good. Thank you to Thomas. Good. The other term. I'll tell you about the PMNS in the next slide. Good. So we've generated a coupling of electrons to neutrinos, muons to their neutrinos, taus to their neutrinos. And this shows up in phenomenology all over the place. So the first thing is what's known as the Fermi constant. So this using these vertices, where did this go? Using this vertex and this vertex, we can put them together and allow the muon to decay, right? So here is the muon decaying to a muon neutrino, an electron, and an anti-electron neutrino. So notice lepton number is conserved. We're starting with 1 lepton. The lepton number of these two is 0 because it's a lepton and an anti-lepton, and then 1 lepton. So even lepton flavor number is conserved here. But we can also derive the size of the coefficient here. Again, I've not derived Feynman rules for you, but let me decorate this diagram with couplings and what we do with this W boson that's propagating from here to here. So here this will be proportional to 2 powers of the coupling of the W boson, which is G. There was a G here, which I did not write down. Now it's proportional to G. Again, I'm sloppy about factors of 2 and the square root thereof. And this W boson propagates from one point to the other, which in perturbation theory, once you write everything out, will contribute this sort of propagator. Now, the P is the momentum flowing through the W boson. This momentum is going to be of order the muon mass, because that's the amount of energy that's being distributed among the decay products. And the mass of the W boson is 80 GeV, the muon is 0.1 GeV. So this term will highly dominate. What does this mean? It means that, first of all, W boson, I was speaking in momentum space. In real space, it means that the W boson essentially doesn't propagate very far at all. And we can contract the W boson to a point. So this is the famous 4 fermion interaction. It's a W boson that's traveling nowhere at all. It's traveling 1% of a Fermi, if you like. So the muon is decaying at a point to its decay products, and the coupling, which we call G Fermi. So this is now a dimension full coupling. G Fermi is, roughly speaking, G squared over the mass of the W squared. Now remember, the mass of W from a couple slides ago was G times V, so it turns out to be 1 over V, 1 over the VEV of the Higgs. So there's the strength of the weak force, the thing that's powering our sun, for example, is directly determined by the squared, by the size of the vacuum expectation value of the Higgs. So that's G Fermi. Let's talk about the Pms matrix. So the Pms matrix showed up in Pedro's talk all over, because that is what's responsible for changing flavor of neutrinos. So that it's the unitary matrix that drives neutrino oscillation. So where does this come from in this formalism? Remember, the W couples the electron to its SU2 partner, which we call nu-E. It couples the muon to nu mu, and it couples the tau to nu tau. And so far, in principle, I can, if I like, I could have defined, and this is universal, right? So let's add the word universally. So if the couplings are the same, what this means in essence is that I've already chosen a basis for you, right? I could have redefined some linear combination of the electron and the muon, and call that the electron, and the orthogonal one linear combination, call that the muon. And the physics is the same, right? Because the coupling is the same. So why did I pick the basis that I picked? Because the electron, and in a few slides, the electron is going to get a mass. So the mass basis for the electron, the mu, and the tau is the basis that I've decided to already preemptively use, right? So these guys, they get a mass from somewhere, from the Higgs boson, and they pick the basis. Whereas these three fields, in principle, they will be getting a mass from somewhere else that can be misaligned with the basis in which the electrons the charged leptons got a mass. So the mass basis is misaligned here. And the unitary rotation that takes you from one basis to the other basis, one mass basis to the other mass basis, shows up in the coupling of them. If I choose to work in the mass basis, both for neutrinos and for charged leptons, this unitary rotation will show up in the coupling of the W, and that is the Pms matrix, which is again all over Pedro's talk, and that's why he's sitting here in the corner happy. Okay. Good. By the way, a very similar phenomena happens in the quark sector, and that leads to the very rich field of flavor physics. The unitary matrix in that case is called the CKM matrix, Tabibo, Kobayashi, and Moscato. Good. There's an interesting qualitative difference between the CKM matrix and the PMNS matrix, which is that the CKM matrix is a small rotation, right? It's nearly diagonal. The up and the down quarks are nearly aligned, but not quite in flavor basis. Whereas the PMNS matrix is a big rotation. So that's an interesting feature of the theory that one of the puzzles that we were left with explaining. And when we think about beyond the Stator model of physics, it's a hint, if you like. Good. So it's not only Pedro that I want to make contact with. I want to make contact with Kate's lectures and with Guillermo's lectures. And what they are telling you about is the measurement of so-called sevens, right? The coherent scattering of neutrinos with a nucleus, and that is a neutral current interaction. So here again, I committed the same sin, so I'm going to, these are taus, tau 1, tau 2, tau 3, and tau 0. There you go. My conscience is clear. So we would like to also derive the coupling of the Z, the neutral gauge bosons in general to the neutrino. Obviously, we know the photon is not going to couple because it is neutral. The neutrino is neutral. So we just go through the same process, and now instead of picking the off diagonal piece here, we pick the diagonal piece which lives both here and here. So things are just a little bit more complicated, but not too bad. And so I'll write down the result. You can see that the neutrino will couple. It's in the top row, so there will be a plus sign in the coupling to the to W3 or W0, right? But there will be a minus sign in the coupling of the to the B, and that is coming from this, right? The lepton has a hypercharge of -0.5 as we've defined it. And this is important because if that minus sign wouldn't be there, we would know we're making a mistake because the combination, first let's close parentheses, L, right? The combination that is the Z from a few slides ago was, here it is, has a minus sign here, right? So it had better be that the thing that the neutrino is coupling to is exactly the Z and not some linear combination of the Z and the photon, because then we would not be calling the neutrino neutral, right? It wouldn't be called the neutrino, the little neutral one. So everything lines up. This is just, it had to work this way, right? But this is just saying that I wasn't entirely, at least I made an even number of sign mistakes in the right places. So this is the Z. And indeed, this is mediating the coupling of neutrinos, E, mu, or tau, to, say, quarks, which live inside a nucleus. Okay, so this will mediate sevens. They write sevens this way, right? And the neutrino does not couple to the photon, so Kate is happy here. And how do I draw Guillermo? A little bit of a scruffy beard. Yes, they're my friends, so I can draw their pictures. So they're happy. And we've made contact with their lectures. Good. How are we doing with time? Good. Halfway point. Fantastic. Questions about the coupling of neutrinos to gauge bosons before we switch gears and talk about fermion masses? Okay, sip of coffee and we'll proceed. Good. So we've given masses to, how about the mechanisms of a neutrino to get a mass? I promise we'll get there. Mariano. That's that's dessert for today. That's where we'll end up. And one of the, as I was writing these talks, I was realizing that so most of my day job is to think about beyond the standard model physics, so I tend to think about hypotheses, things that could happen, but the standard model is this is real. So it gives me great pleasure to have the assignment of teaching something that this is it. This is the universe. But neutrino masses still has this this uncertainty about it, and we'll get to it as to even qualitatively what are neutrino masses like, Dirac, Miranda, all that stuff. We'll get to it. So uncertainty also gives me a lot of satisfaction. Good. So let's talk about fermion masses in general, and we'll start with the standard model fermions other than neutrinos. And the first qualitative statement, so we'll start with a little bit of cartoons again, and move up to equations. The first qualitative statement I'd like to make is that the mass of a fermion must mix its helicities together. It must mix left and right. So left and right cannot stay decoupled and have a mass. And let's do an experiment to prove that. So here's a particle, a fermion, right? And let's say that this is a right-handed fermion, which means its momentum is going somewhere, and its spin will be, okay, sorry, these two are not exactly parallel, but we'll have to make do with that. So its momentum is pointing a particular way, and its spin is pointing in the same way. And I actually don't remember if right-handed is when they're aligned. Maybe that's left-handed, but That's just a name. So the fact that this is a right-handed particle, this will not change if I do a rotation, right? So if I do a rotation, if I do a translation in space, this is still right-handed, right? But not for boosts. Right, so if I boost the system, this particle doesn't have to stay right-handed. So for example, and if this particle has a mass, remember only massless particles travel at the speed of light. If this particle has a mass, it is traveling at a velocity that is less than the speed of light. So let's write that down. Which means that I can get in principle in a car or a rocket or whatever. These days, the private sector is even building rockets for us to travel in. So we pay a lot of money and get into a vehicle, and we in principle can overtake this particle. So the argument I'm going to make here is classical. So let's if this was a spinning top and it's spinning and it's traveling through space and it's traveling in a right-handed fashion. If I overtake it, what will happen? It'll be moving in the opposite direction from my frame of reference, right? But it will be spinning the same way, right? Right, so this is now left-handed. Okay, so now, and notice if this particle did not have a mass, I would not be able to get in a rocket and overtake it. And so there's this connection between mass and this mixing of left and right. Okay, so now I gave you this very hand-wavy, and this was a classical argument. I was sort of cheating. I was starting to make a point about quantum field theory, and then in the middle I said, well, let's imagine this was actually a spinning top, right, which is a classical object. So I'll just state that in quantum field theory, massive particles they're in a superposition. Right, this is quantum mechanics. Things can be in a linear superposition. A superposition of what? Of left and right, right? And indeed, a particle at rest can be in a maximal superposition of left and right. And again, remember in the last talk yesterday, I told you that all these gamma matrices in quantum field theory for fermions is meant to take care of the addition of degrees of freedom. The spinor formalism has a lot of inner workings in the definitions of spinors, which take care of this for you. So so this is not something that we think about when we do computations in quantum field theory, because there's the notation has been very cleverly defined to take care of this linear combination for us and how spinors transform under boosts. It's already built into the formalism. But heuristically, if you open, say, chapter 3 of Peskin's book, you'll find the definition of spinors, and you'll see that very heuristically, a massive particle will be left-handed, but it will have it'll be a superposition really of left and right-handed, and there will be the amount of right-handedness, say, in a left-handed particle will be suppressed by the mass over its energy, right? And we can normalize this by something if we like. So this is just a sketch of how things go. So when a particle is at rest, it becomes a maximal superposition of left and right. And indeed, when a particle is at rest, we shouldn't be talking in terms of helicity. We should just pick a direction and measure spin along, say, the z-axis. Only when a particle is moving do we say, the motion has picked a direction for us, and we measure spin along that direction. Good. Okay, so that means there's a connection between the mass, fermion masses, and symmetry, which is that, so I've written the following statement, that any fermion mass is quote unquote protected by a symmetry. So first of all, these words of something being protected by symmetry, what do I mean by that? It means that if I have a parameter, apologies, if I have a parameter that as I take it to 0, a symmetry is restored, it means that that means the symmetry is protecting this parameter, in the sense that if I set it to 0, it will not be regenerated by dynamics somehow, because the symmetry is protecting it. And this means that, for example, in quantum field theory, if I have a fermion of a particular mass, I don't need to do any fine tuning in order for it to get that particular mass. There are no drastically unesthetic cancellations that need to happen. For the fermion and the fermion mass, so the electron mass is quite small. This is a global chiral symmetry, right? So if I were to, so this is helicity number, if you like. Every time we have a symmetry, we have a conservation rule. So if I have a chiral symmetry which rotates the field by a phase, like so, and I choose to rotate left-handed helicity the other way than right-handed helicity, that means left-handed particles will get a charge and the right-handed particles will get the opposite charge. We call this a chiral symmetry. Or you could call this helicity number, but we call this a chiral symmetry. We never call it a helicity number. And this would be conserved, and a mass would break this symmetry. So fermion masses are said to be technically natural because of this. Just as an aside, and I can't help myself, even though this is not about neutrinos, so this is just a side thought, if you like, thought bubble. What about scalars? And in particular, the Higgs. We just said that the mass of a fermion is protected by a symmetry. And we use these arguments about spin. If a particle has no spin, there's no symmetry protecting its mass. So this is known as the hierarchy problem. And this is employed the minds and employed in the sense of employment of many theorists, myself included. So it is a question as to, so for the Higgs boson, it is not true. In order to have a mass or a vacuum expectation value for the Higgs boson that is much smaller than, say, the Planck scale or whatever it is that the scale at which our theory is defined, I do need to do a fine tuning. So that is why, for example, theorists invented things like supersymmetry. And composite Higgs to explain the mass scale of the Higgs boson, because there's no symmetry protecting it. What supersymmetry does is it says, well, fermions are protected, scalars are not protected. Let's invent a symmetry that connects scalars and fermions. And now the scalars will be protected by this chiral symmetry through supersymmetry. So that's what supersymmetry is about. So this was an aside. But again, I couldn't, because this is such a central puzzle in this day and age, and for the past few decades, I couldn't help but say something about it. Good. So the fermions are protected, the mass of fermions are protected by chiral symmetry in general in quantum field theory. But remember, in the standard model, it's even worse, right? The gauge symmetry is chiral, right? So we just talked about this odd symmetry that I would define the charge of left-handed particles one way and the charge of right-handed particles that way, and that sounds weird, actually, right? Spinning tops usually have the same charge as no matter which direction they're spinning, and taking that to the quantum level is our intuition would think that theory would be odd, but there's nothing wrong with a theory like that. And in fact, the universe is described by such a theory. So I've shown you this charge assignment yesterday, and I didn't pause on it for dramatic effect, but look here, the left-handed fields have one set of charges, and the right-handed partners of these fields, which are these are the guys that are going to intermingle with these guys to give these particles mass. They have a different charge. So this means that if these gauge symmetries would be unbroken, none of these fermions would be able to get a mass, because left-handed particles would not be able to mix with a particle that has a different charge, right? So in order for standard model fermions to get mass, the electroweak symmetry must break, right? But it did. The Higgs broke it for us earlier in today's lecture, also yesterday. And notice this is not true for color, because as far as color was concerned, these had the same charges, and these had the same charges. So color can stay intact and things can get a mass. But for electroweak theory, for SU2 and for U1, that is not the case. So the interactions by which, and also the fermions, in order to get a mass, they must know about electroweak symmetry breaking. So the mass is given to fermions via Yukawa interactions. So interactions of fermions with the Higgs. So here they are. These are interactions of fermions to the Higgs boson, the scalar phi that we've added. By the way, just because wherever I pulled that big equation from, they called the Higgs phi. I adopted that notation. Often the Higgs is called H, and I think even in my own notes I slipped into that. So that's what I'm used to calling it more. So do not be alarmed if you see ELH instead of EL phi. That's important for me to warn you. First of all, let's convince ourselves that these are indeed invariant terms. So for example, let's look at this one. This is a left-handed antiquark and a quark. So in terms of color, the color indices can contract with one another, and this can be invariant. The SU2 indices will be contracted between Q left and phi, right? And up here, I've made some definitions. And in fact, we can use epsilon tensors in order to contract these indices. So I apologize, I swapped notation here. I was a little bit sloppy in terms of whether the VEV comes up or comes down, but I can always, if I have a 0V and I multiply it by the epsilon tensor, which has a 1 and the -1 in the off diagonal, I can get a VEV in the top component instead of the bottom component. So things work out. And the minus signs are not of importance here. Good. So SU2 indices are contracted like here and like between the left-handed doublet and the phi. There's also the hypercharge, which, let's see, this was a 6. Feel free to check me. This is a +0.5, right? The minus was for the lepton, and this is minus 2/3, right? Yes, here it is, minus 2/3. So, for example, this coupling is kosher, and the same is true for the other ones. This phi with a tilde is the complex conjugate. So phi with a tilde has the opposite charge than the phi. So, for example, this, just to show that this gives a mass to the electron, let's write out this term. This will be a YE. There will be a new L and an EL. And here I'm writing this as a row and a column. But this may be, you can use an epsilon to contract 2 rows or 2 columns. So obviously, this will couple. Oh, and there's an ER bar. So this will be proportional to YE times V. E right, E left. And then we call this the electron mass. There's a factor of square root of 2 here that I'm dropping. So the electron gets a mass. By the way, the mass of the electron is half an MeV. The VEV is 100 GeV. As it turns out, there's a small number in the theory. So the smallest Yukawa coupling in the Standard Model is the electron Yukawa, and it's 10 to the -6. This is okay. On some days, I'll get to the, I'm noticing the question just now, I'll get to it. So the Yukawa couplings in the Standard Model are distributed sort of evenly on a log scale. Good. I'm reading the question. Can you spontaneously break any gauge symmetry? What experimental signatures are there to see that the full SU3 cross SU2 cross U1 is not broken? So yes, you can break any gauge symmetry spontaneously. All you need to do is to take a particle that is charged under said symmetry and break it and give it a vacuum expectation value. And this places constraints on theories. So in for example, in models of supersymmetry, there are many new scalars in the theory, and some of them, for example, carry color, like the squarks. And when we write down the theory, it had better be that there's no minimum, at least not one that we can tunnel to faster than the age of the universe, that in which one of the squarks can get a vacuum expectation value, because then gluons would have a mass. So that's your first question. Yes, you can break any gauge symmetry spontaneously. Another example, by the way, is superconductivity. In a superconductor, the U1 of the photon is broken spontaneously by the condensation of a scalar. The scalar is the field, which is the Cooper pair. Okay, so this phenomena doesn't happen only in particle physics. It happens in condensed matter physics. So it's a very interesting phenomena. What are experimental signature that we see the full S? Okay, that's a bit. There's a lot of experimental signatures, but we do know that the couplings, the masses of the W and Z have been measured, and they adhere to the prediction of the Standard Model. The couplings of the W and Z have been measured, and they agree with the prediction of this theory. Gluons have been observed in hadron collisions as jets. So it's I'm not sure if I know what the most direct okay, let's take the theory and do this transformation on it and see that it is invariant. I'm not sure if I know what the most direct experimental test of that is, but this theory has gone through an astounding number of checks and cross checks. So that's too short of a question to a long answer, but I want to get to neutrino masses. Good. Just as, by the way, this line of Yukawa couplings, these are all matrices because remember, there are 3 copies of everything. So really what's going on is that ER bar, mu R bar, and tau R bar is coupling through some Yukawa matrix to a column, and I'm deliberately leaving a lot of space between them, E left, mu left, and tau left. This, in principle, Yukawa matrix can be completely off diagonal. There's no symmetry that's prohibiting me from populating this matrix fully, but I can redefine my fields. And that was when I said earlier that the electrons pick the mass basis. This is a general matrix. It's not even Hermitian. But any matrix can be diagonalized with a biunitary rotation. So I can multiply by unitary matrix on the left and another unitary matrix on the right. Like so. Now I can pick this to be a diagonal matrix, and that will determine what basis of fermions I am going to work with. And it's this rotation that is going to come into the coupling of the W, because remember, this in the standard model, only the left-handed field here is charged under SU2, so only left-handed fermions couple to the W, in case I didn't mention that. Good, so this is where all of flavor also comes from. And the same happens in the quark sector and the CKM matrix. Finally, in the last 15 minutes or so, let's talk about the neutrinos. And here we're starting to go beyond the standard model. Why? Because, again, flashing the particle content before you, notice, so for every Q left, there was an uptype. For the Qs, there's Q left has an up and a down quark. And then we added a right-handed partner both for the up and for the down. The left-handed lepton has an electron and neutrino. We added a right-handed electron, but we did not add a right-handed neutrino. Why? Just because, right? This is how we're defining the theory. We're about to add one, don't worry. It's an obvious thing to do. But as we've written it, there's no new R. And so E left needed ER in order to get a mass. With this field content, at least, up to dimension 4, right? We've written down all of the dimension 4 and below interactions that we were allowed. The neutrinos are massless. So that's not bad, that's a very nice prediction from the standard model, because the neutrinos are almost massless, so it's a good starting point, right? Now, obviously, so something, but now we know neutrinos do have a mass. So something here needs to be violated in these assumptions. Either there is a new R, or we need to go beyond dimension 4. So we're about to explore both of these options, but we'll leave no stone unturned. Notice that in the standard model, still adhering to up to dimension 4, the interactions that we've written down, and this field content lepton number is an accidental symmetry. So that is to say, let's go back to first slide of today. Here are all of the dimension 4 interactions that we could have written down. And as it happens, we did not, so we write all of them down, and then we notice, there's no symmetry that violates lepton number. So every time a lepton appears, say here, an anti-lepton appears. So I can decide to rotate all leptons by a phase. This term is symmetric. Here is another lepton. This is symmetric. Check and see. The only thing we've imposed is the gauge symmetry, but there's this global symmetry that is there accidentally. good. Let's go back to where we were. Where were we? Here. Okay, so now there are two options for this the fate of lepton number. Either lepton number at short distances. Remember, accidental symmetries is the symmetry that we see. That's the story with a spherical cow. From the top of the Fitzroy Mountain, all the cows in the valley look like points and are thus spherical, right? So, but if we get closer, will the cow remain spherical, or will it have some more symmetry breaking structure? Equally, if I zoom in on the dynamics of the Standard Model at short distances, will lepton number break or not? Okay, so option number one, lepton number is preserved. In that case, we will, in order to give the neutrinos a mass, we will need to acquire a partner, right? Because fermion masses must marry left and right. So we need a new R in the theory. And then we call these Dirac neutrinos. Dirac. So, and all of the other fermions in the theory are Dirac fermions. The fermions that have essentially 4 degrees of freedom: particles, antiparticles, left and right. The other option will be that the lepton number is broken. So zooming in on the cow, we will find symmetry violating features like a tail and horns. And this will manifest itself in the effective theory of the Standard Model as higher dimensional operator. And in fact, we will not have to go far in this. Remember, we truncated dimension 4. So now we'll say, okay, let's keep going in this expansion until we find something that violates lepton number. And as it happens, we won't need to go far. We'll find it already at dimension 5. So this will happen at dimension 5. And I'll tell you very briefly about what's known as the seesaw mechanism. But these are called Miranda neutrinos. This morning, I realized I did not prepare a slide about Miranda neutrinos, but Miranda neutrinos are different from Dirac neutrinos in the sense that they are their own antiparticle. So they have only 2 degrees of freedom. There's a left-handed particle, a right-handed particle, but the left and the right are the antiparticles of one another. They're their own antiparticle. So 2 degrees of freedom less. So we don't need to add this new R. Okay, new left has 2 degrees of freedom. We're going to marry the new left with the anti-new left, which is a right-handed particle. Okay, so there were 2 options. Let's do them one at a time. First, Dirac neutrinos. So we're going to add, so this will be very familiar because it's just like the other Dirac fermions, the leptons. So we're going to add a new field, which is new R. Right, so there was no new R here. And what will be its quantum numbers? Well, it better not be colored. It will not be charged under SU2, like the other right-handed fields. And it will not carry any hypercharge. So this is not charged under anything. It's just the most neutral, bland particle you could imagine. And now we can write down a I've moved the stuff aside to make room. Here is our new friend, the right-handed. And then this couples to that. I've already expanded it here. So this is very much like there's something pleasing about this in the sense that the neutrinos are just like the rest. So whether you prefer Dirac or Miranda, that's a matter of taste. And myself, I'm on most days I'm a fan of Miranda, but on some days I'm a fan of Dirac. In this theory, the mass of the neutrino will be just the Yukawa of the neutrino times the VEV. And here's the unpleasant part. The Yukawa will need to be very small, 10 to the minus 12 or so, right? So does that bother us? Yeah, it probably should, right? We don't want to input, but maybe we can come up with a theory for why this Yukawa is small, and people have that. Models of extra dimensions, Froggatt-Nielsen models, there are plenty of ways to generate such small numbers. And again, just for perspective, recall YE is 10 to the minus 6. So we already had to swallow a small number. So this is just twice as small on a log scale. So this is a line in the sand from the aesthetics point of view. And again, just to make contact with Pedro's next talk, so he and I have coordinated, we've colluded. This will be important for phenomenology because lepton number is conserved, and there will be a process called neutrinos double beta decay. And if we observe it, we will exclude this possibility. Okay. Okay, on to Miranda neutrinos. So now we're not going to add a right-handed neutrino, at least not to the spectrum of light particles that we see. So notice in the standard model field content, we can take this particle, this guy and that guy. They have the same color charge, which is no color charge. They both have SU2 indices, but those we can contract with one another with an epsilon tensor, and they have opposite hypercharges. So if we write L times phi or L times H, and for some reason I'm used to calling this L8 squared, the operator, so I'm going to switch from phi to H. L times H is an invariant under the gauge symmetry, right? This is still a fermion because the Higgs is a scalar, L is a fermion. So now I can take two fermions and contract them together. The Lorentz index, the spin index can be contracted. So if I can take two of these, this is an invariant. The only thing that I violated is that I went to the next order in the multiple expansion of this field theory, if you like. So I will need to introduce a dimensional coefficient, and it has a coefficient of 1 over mass. So 1 over the cutoff. So first of all, what does this do? Just let's write it out. This is nu L EL contracted with a VEV, and trust me, with the epsilon tensor contracting, the VEV comes up in the right place to give the neutrino a mass. To just pull out the neutrino, and I square this. So this is just V squared, the VEV squared, over this scale times nu L. So a few things. This violates lepton number, right? Because this is neutrino. It's not neutrino antineutrino. which is fine. It does mix left and right. I do not have time to show you this. But this is what a Miranda mass is. It is a mixing of left and right, but for the same particle. And this is only possible for neutral particles. So a charged particle cannot get a Miranda mass. It must be a Dirac particle. Since the neutrinos are the only neutral particles we know of, at least in the effective theory, they're the only ones that can get a Miranda mass. The other interesting thing is that in order to explain the mass of the neutrino, if there's no other small number in the theory, what does this scale lambda have to be? Well, it turns out it has to be 10 to the 14 GeV, right? So this is a very high scale now. In order to, you see this very large scale is appearing downstairs and it's pulling the masses of the neutrinos down. So remember the multipole expansion, we looked for something from very far and its size, let's say, is lambda inverse. At the scale lambda, we would be able to resolve its structure. So it does beg so we've added in a higher dimensional operator, and it does beg the question. I'll be done in like 2 minutes. It does beg the question of what is the physics at the scale lambda. So the seesaw mechanism is perhaps the nicest explanation of what's going on, which is at the scale lambda, I'm going to add the same, something very similar to what we did in the Dirac case. We added a right-handed neutrino. Let's add a very heavy right-handed neutrino instead. So we add a heavy singlet, and we could call it NR. And then we couple it, oh, there must be some bar here. We couple it to, like the Dirac case, to the Higgs and to the lepton, like so. And we give it a very heavy Miranda mass. So this is going to violate lepton number, this Miranda mass. But again, we did not impose lepton number in this model building story. And we're going to say that this mass is of order lambda, of order 10 to the 14 GeV. So this is close to the gut scale, very heavy. And as it happens, this will give a mass to the neutrino through a process like this. The lepton goes to this heavy N with mixes with the opposite helicity, so that's the mass, going back to L, and this will be proportional to Vev insertions. So this will so now, first of all, this N, like the case for the heavy W, does not propagate very far at all, so I can quote unquote integrate it out. I'm slipping into jargon at the end. But this will give me effectively this operator, L, H, H, L. So this is the LH squared operator. This is called the seesaw mechanism because the heavy neutrino is so heavy, it pulls the mass of the other neutrino down. So, and this can, so basically the fact that the neutrinos are so light in this picture is telling us something about the presence maybe of a new field at a very high scale. And that lepton number is violated at that very high scale if we're able to resolve. It's the first effect that is resolving these small scales. Good, so I'll just very briefly summarize these 3 lectures. We talked about quantum field theory, and we talked about the Standard Model, which explains to the best of our ability the question of how does the universe work. But again, I've sung the praise of the Standard Model and how fantastic it is, and it is. But there are many, but it isn't complete, and that's a lot of what drives us to think about this so much. And so here's a list of things that we're still curious about. So the neutrino mass is the first hint that the Standard Model is not the minimal structure that I gave you. That's not all there is to it. But there's also dark matter, dark energy, the tuning of the electroweak scale. That's the Harnik problem that I mentioned, the strong CP problem, the flavor structure, the unification of 3 to 1 maybe to a bigger group. So we have all sorts of interesting ideas. So I would say that there's a lot to explore. Great, thank you. I'm happy to take more questions, and if not, we'll get some coffee before Pedro comes in.
Thanks a lot, Roni, for this wonderful talk. Let me say one more time, thank you for agreeing to be part of this school.
My pleasure.
Okay. So, any question? Any comments?
It's pretty late, but I was going to ask Roni what's the status of an experiment that tried to see if neutrinos are Majorana or Dirac, or I don't know if that's going to go in another talk from Pedro or whoever.
Pedro is planning to talk about neutrinoless double beta decay. And so these are the experiments that are trying to tackle this question. So they're ongoing. And I think Pedro will cover that. At least we exchanged texts yesterday, and that's where we drew the line between us.
Okay. Any other question?
So yeah, I have a question. Just a second, Dario. So if neutrinos were Dirac particles, right?
Yeah.
You put them on this list. Is that okay? You would put it within the Standard Model because it would fit just a Standard Model, except that these are particles that only appear through the interaction with the Higgs.
Correct.
That's true, right?
Yeah. So you're and even I wasn't entirely consistent throughout these lectures about asking, is this part of the Standard Model or not part of the Standard Model? So this is a little bit of a question of taxonomy. What is beyond the Standard Model physics? If you define the Standard Model as this particle content up to dimension 4, then neutrino masses are beyond the Standard Model. You could decide, okay, new Standard Model. Here it is. I did it. Now there is room for neutrino masses, but it is true that on the day that you discover the mass of the neutrino, you discover the existence of a new particle. The strange thing is we don't know if that new particle is at the mass of the neutrino, in which case it's the right-handed neutrino, or maybe we discovered a new particle at 10 to the 14 GeV, and we don't know which one it is. So in that sense, because there's still some lingering uncertainty here, this is still within the realm of beyond the Standard Model of physics. So I'm happy to subscribe to both factions that say that this is a small extension of the Standard Model. We might as well call it part of the Standard Model, and the faction that says that this is beyond the Standard Model of physics.
Okay, I didn't know there were factions about it. It's just a doubt I always. Okay.
I don't know if it's this is not a very hot debate, but some people will say that okay, the Standard Model already has neutrino masses in it. Say, just add one more. Just say that you're going up to dimension 5, and then it has neutrino masses. But still, we still don't know if it's Dirac or Majorana, and if the new particles show up at the sub-eV scale or 10 to the 14 GeV scale. So that there's no debate about, that we still don't know.
Okay, thanks a lot, and I join Dario in thanking you for these lectures.
My pleasure.
Yeah, for sure, this lecture will be the reference material for future students. And let me confess that today, every time you drew a point, I saw a cow. This is a proof that how you changed the mind of the people.
By the way, one more question. Were you really up in the Fitzroy?
No. I went to no, I was not. I did not climb the Fitzroy.
Okay,
I did it.
That was very impressive.
Yeah, I saw the Poreto Moreno, and I did a trek in Torres del Paine, but I did not. I'm not that serious of a climber. I enjoy the view, but yeah. Similarly, climbers at the top of Fitzroy also look like spheres, so that may be a better a better analogy for accidental symmetries. There it is.